Sum is a constructor for evidence for a proof object that, and now it takes 4 arguments, 2 numbers and 2 proofs. So when applied to n, m, a proof that n is beautiful and a proof that m is beautiful, it yields, or we should better say it is, that expression is evidence that n plus m is beautiful. Okay? So now we can prove theorems about beautiful numbers. So here, for example, is a theorem that says 8 is a beautiful number. And we can use all the same tactics that we're used to because Coq is very orthogonal. So the fact that this is an inductively defined, the fact that these things are constructors rather than theorems that we proved is immaterial. We can apply them because they have the right type. So if we're trying, so here we're in a proof state where the goal is beautiful 3. Up there we have something of appropriate type. That's all apply needs. So it unifies beautiful 3, which is the goal state, with the conclusion of the type of the axiom that's being applied. It is only a conclusion. It's not a hypothetical thing. So the conclusion is beautiful 3. What we need is beautiful 3. Done. Okay, so we can use apply and other tactics, perhaps, with these inductively defined propositions. Okay, now we might wonder whether instead of apply, we could just say, well, if what I need is evidence that 8 is beautiful, why can't I just build that myself? Why can't I just build the term? What term would it be? It would be this one. B sum applied to 2 numbers and 2 proofs. And indeed, if we check the type of this term, its type is beautiful 8. So if we're trying to prove 8 is beautiful, we can just say apply this. Okay, so this is showing that apply is even a little bit more general than what I've said. Instead of applying a named thing, we can also apply an anonymous thing that we've constructed right here, as long as it has the right type.
Do you think Coq would infer 3 and 5 here?
Coq might, in fact, infer 3 and 5 here. So this would be a good place to try inferring non-type arguments by putting underscores there and there. I'll bet it would get it. Yes. So we're going to see some other tactics that are useful with inductively defined propositions, and inversion will be one of the main ones. That's right. So writing out explicit proof terms is what you'll see when you watch experts driving Coq is that for small things like this, where they can say, oh yes, I just need to combine the constructors like this, they'll just do it and they'll write the expression. For bigger things, they'll usually use tactics.
So inversion means translate into something like this. So the proof term will be the
Yes. Yeah. So a complicated proof involving inversion. I'm hedging a little bit because inversion is a kind of a complicated beast. Some proof involving inversion might translate into this, but on the fly, I'm not sure. Other questions? All right. Okay, let's actually look at this. What's that file? Plot.v. beautiful. Right, so if we're in the middle of doing this tactic proof, we can actually see the incomplete term that Coq is constructing. So I asked you a few minutes ago to forget about the low-level terms that were actually the realizers for that Coq was building. Now let's look at them. So we can see the proof state. So here we're in a state where we've applied B sum, and notice that we needed to tell it what n and m were because that wasn't determined by unification. And now, if we do show proof, this shows us the term that Coq is in the middle of building. So the term is B sum of 3, 5, and question mark 1 and question mark 2. So question mark 1 and question mark 2 are the subgoals. Those are the places in the incomplete term that are still incomplete. And their types are beautiful 3 and beautiful 5. Okay, so this is not usually a useful thing to do. It's just I'm lifting the hood a little bit to show you what's actually going on underneath, and it's occasionally interesting to do that just to get a sense of what are these proof terms that Coq is trying to build. Okay. Now, what can we do with these proof objects, these concrete bits of evidence, these terms? Well, we can build them up. We've just seen that. But we can also break them down. This is a very interesting consequence of the kind of Curry-Howard isomorphism, the fact that these proof objects are data. That means that everything that we can do to data, we can do to proof objects. In particular, we can recurse over it. And what is that? It's doing induction on derivations, right? Because a proof object is a derivation tree. A proof that some number is beautiful is a derivation tree in the tiny little four-rule logic that I defined for reasoning about beauty. And we can do induction on those derivations. So, for example, here is a different property of numbers. This is the property called gorgeous numbers. So this property says 0 is gorgeous. If n is gorgeous, then 3 plus n is gorgeous. And if n is gorgeous, then 5 plus n is gorgeous. Okay, so it's just a different property of numbers. And what's interesting, though, this is an actual slightly interesting mathematical fact, is that every gorgeous number is beautiful. How would we prove that? Well, not by induction on numbers, but rather by induction on the reason why, the evidence that a particular number is gorgeous. So, in this proof, let's quickly look at it here. Oops. In this proof, so we intros a bunch of stuff. By the way, if you say intros and you don't give any names, it will just choose them for you. Sometimes that's what you want. So we're going to do induction on H here, which is evidence of something or other, but more concretely, it's just a tree, right? It's a tree data structure. So we can do induction on it. And we get 3 subgoals. Why? Because the gorgeous data type has 3 constructors. So we have to show that 0 is beautiful from no assumptions. We have to show that, which is easy, we have to show that 3 plus n prime is beautiful given that n prime is beautiful, and so on. Right? So this is just kind of the induction, this is following the induction scheme that arises from the definition of gorgeous is what's happening. Okay. What about evenness? Could we have an inductively defined proposition for even? Of course we could. Here it is. 0 is even, and if n is even, then 2 successors of n is even. All right, this is just exactly like the definitions of beautiful and gorgeous. There's a different way of defining even, though, because we've already been talking about even. We have this function that checks evenness. So we define the property of being even. So a number is even. We can define to be the function even b returns true when applied to that number. Okay, so that definition up there, that's a definition of a parameterized proposition. Not an inductive definition, but a direct definition that says the proposition even of n is the expression even bn equals true. Now, there's something subtle going on here. We have 2 different definitions of evenness. In fact, we have 3, in a sense, definitions of evenness. We have the evenness checker, which is a function that returns a Boolean. What do Booleans have to do with truth? Nothing. They're just a data type. Right? We happen to call it Boolean, and that happens to have some connection in our minds with classical logic. But so what? Right? We could have called it foo and called the constructors red and green, and we would still be doing the same computation. Okay, so that's a function that returns an answer in some data type that we happen to have called Boolean. Now we can define the property that is the parameterized proposition, the family of propositions, that says a number is even. I'm defining the concept even by that test returns true. Or I can define it directly in as an inductively defined proposition. Right, so we have all 3 of those things. Which is better? Okay, good. So the reason why the first definition is better. So my answer to which is better is both. Why is the first one better? The first one is better because we defined this recursive function that calculates on numbers, and if we apply it to a concrete number, we can simplify it. And so the simplification, the definitional equality mechanism of Coq is doing work for us. And we're not going to get that in if we use the inductively defined proposition version. Right? So for example, I think it says this down below. The fact that even b of 1,000 is equal to true is by reflexivity. Right? That's the proof object for that equality. And yes, Coq has to do some work to check it, but the proof object itself is tiny. And that can be quite convenient when you're doing proofs. It means that you don't have to do a lot of fussing around and saying, well, no, 1,000 is even because 998 is, but that is even because 996 is. So you don't have to do all of that messing around. That also gives us, well, you can get, each of these files comes with its own proof terms. The proof terms for this proposition defined in terms of a computational fixed point can be a little easier to work with because Coq is doing the unfolding under the hood. Whereas with the inductive definition, there is no kind of built-in unfolding. So if we want to show that 1,000 is even, we have to show it by building the proof term ourselves or writing a tactic that does it or something. However, the inductive definition is also better. Why? Because it's lower level. And lower level things sometimes work when higher level things don't. So in the case of even, we saw that both definitions work. Right? So you can define it via computation, you can define it inductively, and indeed we will show a little later in this file that they define the same property. They define the same property of numbers. So you can show that if n is EV even, then it's EVEN even, and vice versa. And people actually do that. So you may find it convenient when you're working with a particular concept to define it both computationally and inductively and to show that they're the same. And then you can switch back and forth between the points of view. And that's sometimes convenient. There are cases, though, where it isn't convenient or even sometimes possible to define it computationally. And we've seen two of them already. What were they? Beautiful and gorgeous. So if you look at this, I'm going to say beautiful and gorgeous. This would not translate immediately into a recursive function. We might be able to find a recursive function that's equivalent to this, but it wouldn't be obvious that it's equivalent. The equivalence itself would require a proof. So if we want to do that proof in a checkable way, we need to be able to write down this definition as it stands. And this definition as it stands can only be written as an inductively defined proposition. So inductively defined propositions can be used to define things that are not total. So it can be used to define non-total functions. It can be used to define things that are not functions at all. It can be used to define arbitrary n-ary relations in general. And we will use that fact very heavily as we go on. So in some sense, the lower level and more useful one, more generally applicable one, is inductive definitions. Fixed point definitions are the one that occasionally works, and it's nice when they do. Okay, let's break here.